In this lesson, we'll look at driver libraries. And by driver libraries, I mean hardware driver libraries. We'll first discuss the use of abstraction in driver libraries. This is an important part of these libraries. Then we'll compare the driver libraries provided for our STM32 MCU and packaged within the IDE we're using. Now this is just an example. Other MCUs and MCU vendors will have different libraries. Anyhow, for our MCU, we have the low-level or LL library, the hardware abstraction layer or HEL library, and the CMSIS library. And I'll tell you what CMSIS stands for later on. And then I'll give some views on the use of these driver libraries based on my experiences. Now I have some notes on terminology in this box below. In this lesson, the term core hardware refers to the CPU and peripherals tightly coupled to the CPU, like the interrupt controller, floating point unit, system tick timer, and some others. Note that this hardware is described in the ARM level documentation, not the ST microelectronics documentation. And I'll use the term peripheral to refer to non-core hardware like the UART, I2C, DMA controller, and others. This hardware is described in the STM microelectronics documentation, such as the MCU reference manual. Now let's talk about hardware abstraction. Abstraction is a fundamental concept in computer science. It is used everywhere, and much of the success of software systems is based on the use of abstraction. It's yet another method to divide and conquer. The idea behind abstraction is that lower layers of software hide the details and present a simpler model of the world to the upper layers. In this case, the model is a hardware device. This simpler model is presented via the library API. The model might not be explicitly described, but it is there in the API. Now, developers of the upper layer software can then focus on higher level concepts and not worry about the low level details. The hope is that this results in simpler software that costs less to develop. And there is a possible bonus. Sometimes you can have different flavors of the lower level or lower layer software, for example, for different hardware, that present the same model, in other words, the same API, to the upper layer, making the upper layer software portable. This is the dream. Sometimes it works, sometimes it doesn't. So this abstraction thing looks great, but here's the rub. It is difficult to design libraries with high levels of abstraction. First of all, you can have models that are too simple and they will have limited usefulness. People who are going to develop the upper layer will look at that API and just say, no way. Now, to be fair, it is hard for library developers to anticipate the range of needs of the upper layer developers. I've worked on systems and APIs where I thought it was great, and then the first time someone tries to use it, they run into some shortcoming. And it's because I never imagined they would use the API in a particular way. And there's a trade-off between the flexibility of a library and the simplicity of its model or API. What can happen is to make your library more flexible, you keep adding to the API. And so the API gets more and more complex. At some point, someone might look at that API and say, I think I'd rather just do it myself. So here, using this picture, I want to talk about the trade-offs in levels of abstraction in a driver library. So on the left, you see a library providing a lower level of abstraction, and on the right, a library providing a higher level of abstraction. And you could imagine it's sort of a continuum. These green arrows show some beneficial property or characteristic of a library, or of using that library. And the arrows point towards the level of abstraction that provides the greater benefit. So let's look at these properties. The first one is simplicity of the upper layer software, which usually means lower development cost. Of course, the benefit grows as you move towards higher levels of abstraction. You probably have to write less lines of code, and that is always a good thing. On the other hand, flexibility and fewer constraints on the upper layer software improves with lower abstraction in the library. There are fewer times that the developer of the upper layer will look at the API and say this API doesn't really fit with our software architecture. In this case, it's an advantage that you have to handle more details. Portability of upper layer software becomes greater with more abstraction, as you would expect. The fact that some of the details or more of the details are hidden means that different kinds of hardware, for example, will look the same to the upper layer software. Now, these properties so far have been more theoretical, more computer science kind of stuff. Now let's look at some more practical issues. One is a lower likelihood of bugs or hidden implementations in the library. The software provided by MCU vendors is written by people like you and me, and so it can contain bugs. But normally, the simpler the software, the fewer the bugs. And the lower abstraction library might be just setting bits and fields and registers, whereas the higher level abstraction library might be handling interrupts and modifying shared variables. Which one do you think is going to have more bugs? The other issue is hidden limitations, and this goes like this. Say you are working on your project and it's going well, and you need to handle some special case on an I2C bus, and you code it up and it doesn't work. You investigate and find out that the API you are using doesn't work quite the way you expected. It really isn't a bug, it just wasn't mentioned in the documentation. So now what do you do? Well, maybe you hack the library, or maybe you just have to find some workaround. With lower levels of abstraction, this is less likely to occur. Again, the fact that the library does less means there should be fewer surprises. A function whose only job it is to set or clear a bit field is pretty straightforward. There aren't too many possibilities of limitations. And the final property is the library implementation being easier to understand. You might say, why should I care? Well, you care because when there are problems, you sometimes or maybe often need to look into the library. It doesn't mean the problem is in the library, but sometimes you just have to understand what the library is doing to help you find the bug. With a complex library, you might spend hours looking at the code and trying to figure out what it is doing. Now we'll talk about the 3 device libraries. And again, this is specific to STM32. And we are talking about libraries that are packaged within the IDE. The first library is called CMSIS, and it's a vendor-independent library for ARM Cortex. This is unique for the 3 libraries we are looking at because the other ones are provided by ST Microelectronics. Now this is what CMSIS stands for, and I will just let you read that. And the point I would like to make is the word Cortex is right in the title. So this library is specific to ARM Cortex MCUs. The library was created by a company called Keel, which is now part of ARM. It was acquired, I believe, and in any case, it's open source. The library actually has a very wide range of functionality, from MCU hardware drivers to RTOS and neural network stuff. Now in this course, we're only considering the MCU hardware support. And I should point out that other MCU vendors integrate CMSIS with their SDKs. I know I've seen it in the NXP SDKs. So using CMSIS is good in that sense, is that it makes or can make your software a little bit more portable. Now, just as a point of terminology, CMSIS uses the term core for MCU core hardware and the word device for MCU peripherals. CMSIS does provide support for core hardware. Uh, as far as I can tell, it is fairly complete, but I have not used it enough to be able to say that with complete certainty. I can say that the API names are not 100% consistent compared to HAL and LL, where it seems to be a little bit more consistent. But the names often start with the name of the core peripheral. So the APIs for the interrupt controller start with NVIC. I think that means nested vector interrupt controller. System tick, ARM MPU for the memory protection unit, and there's a few others. Beyond the core hardware, CMSIS provides an API definition for peripherals, or what they call devices, which would be things like a UART or a DMA controller. Looking at the API, the level of abstraction, I would say, is similar to STM32 HAL. It's higher level procedures it supports and so forth. However, ST Microelectronics does not implement to this API. I think, of course, ST Microelectronics has a HAL library. I don't know if there are any good implementations. I have not yet found one. Now let's talk about the STM32 low-level or LL library. Now LL is provided by ST Microelectronics, means it's intended for just STM parts. Now I'm going to describe LL by asking the question, at a low level, what do we need to write code for MCU hardware? And here are at least my answers. First, we need the addresses of peripheral registers and the layout of those registers. We need the ability to read and write registers, bits, fields, and complete registers. We need to execute procedures, for instance, make the peripheral do something like an A to D conversion. A procedure might consist of several distinct steps. Now for item 1, the LL library provides lots of defines for addresses of registers. And some of these defines come from CMSIS. It also contains C language structures that represent a set of registers in a peripheral. For item 2, the ability to read and write register data, the LL library provides lots of hash defines for the bits and bit fields in registers, and lots of tiny functions to get or set that data in a register. For item 3, for executing procedures, LL doesn't provide much. First of all, LL is stateless. It just does what you ask, like read or write a register, and once that is done, it forgets it. This limits what kind of procedures it can implement because, as I had mentioned, some procedures consist of a number of steps. Now, LL does provide a few slightly higher level functions for things like initialization, but these are very simple procedures, usually just writing a few registers in one function call rather than writing a single register. And LL doesn't provide interrupt handlers. So in summary, when you're using LL, implementing procedures is mainly on you. You have to orchestrate it. In terms of coverage of hardware, LL supports most, but not all, core hardware, and most, if not all, peripherals. I have not used LL enough to say with confidence whether it supports all of the peripherals. Now, that means LL overlaps with CMSIS and HAL. As you know, CMSIS supports all core hardware, and I know that L supports most, if not all, peripherals. Of course, HAL is a different style of library. On a practical level, most, if not all, LL symbols start with LL underscore. And that's nice because when you see the symbol, you know where it came from. Now let's talk about the STM32 hardware abstraction layer, or HAL library. First, let me say that this library name can be confusing because the term HAL is used generically in the computer industry. Of course, we know in this course that the term HAL refers to this library. So HAL is provided by ST Microelectronics, meaning it is intended for just STM parts. Now, HAL provides a higher level of abstraction compared to CMSIS and LL. This means it has functions that to perform complete procedures like a complete analog to digital conversion or the sending of a message on a UART. Now, HAL handles the reading and writing of registers internally within the library. The upper level software does not need to be aware of these registers at all. Now, in order for HAL to provide procedures, the HAL library uses variables to hold the state of the procedure, as well as buffers and other things. In other words, HAL is stateful compared to the LL library. Now, the HAL library provides support for most, but not all, core hardware and most, if not all, peripherals. Like with LL, I am not certain if HAL supports all of the peripherals, but certainly most of them. And like with LL, there is overlap in coverage between HAL and CMSIS and LL. There are many functions that could be done by all three of these libraries. HAL also provides interrupt handlers when they're needed. And finally, HAL provides support for poll, interrupt, and DMA modes. You'll see this described in the HAL documentation. And it supports event notifications. Now, some of this depends on the exact peripheral you're using. Of course, with LL, you can also do all of these modes, but you have to sort of program it yourself. Here I want to show just a summary of hardware coverage with these three libraries. So for core hardware, CMSIS provides complete coverage. And LL and HAL provide pretty good coverage, but CMSIS might be required for a few things. For example, I don't think LL has APIs for the interrupt controller. Now, this really doesn't matter because if you use LL or HAL, you will also have access to the CMSIS APIs. For peripherals, LL and HAL provide support. Of course, it's at different levels of abstraction. As mentioned before, with the CMSIS device API, there doesn't appear to be a good implementation of drivers for STM32. So it means you need to use LL or HAL or find something else. Now, this diagram below here is just for your information. It really isn't important. It just shows the relationship between these libraries at the implementation level, which I find interesting. First, you can see that all three of these libraries interact directly with the hardware, which is what you'd expect. And both LL and HAL make use of some CMSIS APIs, and that seems reasonable. The thing that is surprising to me is that HAL is not built on top of LL. It seems like it should be. I think that maybe this is for some historical reason. Now in this slide, I'm going to give you my opinions on use of these driver libraries. Notice I put the word opinions in red just to make this clear. So my first suggestion is to use CMSIS for the core hardware, for example, interrupt controllers. LL and HAL both support most core hardware as well, but CMSIS means your code is slightly more portable to other vendors. Next, I suggest to use LL as is for register level programming of peripherals. There seems to be little point in starting from scratch, creating your own hash defines and macros that do the same as LL. Maybe you don't like the naming style in LL, but otherwise I don't see how your implementation would be much different than LL. Now regarding HAL, I'll first say it's clearly suitable for things like board bring up and hardware verification and testing, performance validation and testing, and maybe prototyping for early demos. All of these things can be written with the HAL API in mind, and they are usually not product code. So they don't have high reliability requirements. They just need to work reasonably well. Now, HAL can be suitable for product use, but my suggestion is to be careful. First of all, ensure it is flexible enough for your project long term. Sometimes things seem okay at first, but as the project progresses, you start running into limitations. Another thing is to read the library code and make sure you understand it. Carefully check error handling, interrupt and DMA timing, loops without guaranteed exits. I will admit this is not easy to do. A few of these things can be checked, maybe like error handling. I will admit it would be hard to find timing issues with interrupts and DMA. Now the reason I say this is that I have found problems with higher level libraries. I won't say which vendor it was, but it was things like race condition problems with interrupts that occurred rarely and in some cases were detected late in the development cycle, which is not nice. I didn't want to do a major rewrite of the higher layer software, so I ended up just fixing the libraries. In fact, whenever I found these problems, I would just fix the libraries. And to be honest, I would probably not have spotted these bugs just by inspecting the library code in advance. They were subtle problems. Even when I knew there was a problem, it took some time to find it. So in summary, for new work, I would lean towards using LL. It is more work up front, but at the end, you'll understand your code much better than you will understand third-party library code. And one more thing is to consider another layer of hardware abstraction at the software module level. We'll be talking about this later in this course. So that's it for driver libraries. Once again, thanks for watching.